Data examination is a time-consuming but necessary initial step in any analysis that researchers often overlook. We need to look at graphical examination, identify and evaluate missing values, identify and deal with outliers, and also test for the assumptions underlying most multivariate techniques. The goal of these data examination tasks is to reveal what is not apparent, because the hidden effects are easily overlooked. For example, the biases can be introduced by non-random missing data. Unless the researcher reviews the results on a case-by-case basis, the existence of outliers may not be visible. Violation of the statistical assumption may also cause biases or non-significance in the results that cannot be distinguished from the true results. In addition, graphical examination shows data distribution, range, shape, and also improve our decision-making process in collaboration. First, we will review the key terms to develop an understanding of the concepts and terminology used. Box plot is the method of representing the distribution of a variable. A box represents the major portion of the distribution, and extensions called whiskers reach to the extreme points of the distribution. The box itself represents 50% of observation from Q1 to Q3, which is interquartile range, and dots represent outliers. This method is useful in making comparisons for one or more variables across groups. A vertical line inside the box is location of the median value. Histograms. They are graphical display of the distribution of a single variable. By forming frequency counts and categories, the shape of the variable's distribution can be shown, and it is used to make a visual comparison to the normal distribution. Scatterplots. They are representation of the relationship between two metric variables. And if the points closely resemble a straight line, this indicates that the relation between two variables is approximately linear, positive or negative. The starting point for understanding the nature of any variable is to characterize the shape of its distribution. There are methods for quantifying the lack of symmetry, of skewness in the distribution of a variable. For a symmetric distribution, the bulk of the observations are either to the left or to the right of the mean. Skewness is a measure of symmetry, and more precisely, the lack of symmetry. The formula for skewness is referred to as the Fisher-Pearson coefficient of skewness. It is built upon sample mean, sample size, sample standard deviation. You may see also adjusted Fisher-Pearson coefficient with adjusted sample size. So if the value of skewness is positive, the data is positively skewed or skewed right, meaning that the right tail of the distribution is longer than the left. If skewness is negative, the data is negatively skewed or skewed left, meaning that the left tail is longer. If skewness equals 0, the data is perfectly symmetrical. If we find that the values for skewness are between minus 0.5 and 0.5, it is a fairly symmetrical distribution. But if it falls outside of the range of minus 1 and 1, it is considered to be highly skewed distribution. Compare two distributions on the bottom screen. Skewness for the left figure 0.76 and skewness for the right figure minus 0.39. The negative and positive sign tells you whether it's a positive or negative distribution. And you can tell from the value that the figure on the right is more or less symmetrical because it is within the range between minus 0.5 and plus 0.5. And the figure on the right is more asymmetric. The other common measure of shape is called the kurtosis. Traditionally, kurtosis has been explained in terms of central peak. You probably have seen the statement saying higher value indicate a higher, sharper peak, and lower value indicate a lower, less distinct peak. Similar to skewness, if the value of kurtosis are close to 0, it indicates that the shape of a frequency distribution approximates a normal distribution, which is important for checking assumption in a certain data analysis methods. So if we have negative kurtosis, the value would indicate a flatter distribution, and the positive value will denote a peaked distribution. And remember, kurtosis refers to the height of the distribution, and skewedness is used to describe the balance of the distribution. This normal probability plot compares the cumulative distribution of actual data with the cumulative distribution of a normal distribution. A normal distribution will form a straight diagonal line, and the plotted data value compared with the diagonal. So if the distribution is normal, the line representing the actual data distribution closely follows the diagonal. Let's look at the figure 6. It shows us several departures from normality and their representation in the normal probability in terms of kurtosis and skewedness. I encourage you to pause the video for a moment and review each distribution and compare to normal probability plot. Let's move to bivariate profiling. The graphical method for assessing group differences is the box plot. Box plot is a summary of the distribution with 6 important values: range, quartile, mean, median, minimum and maximum values, and also it helps us identify outliers. So what are quartiles? Quartiles is a continuous variable divided into 4 segments. Q1, 25th percent mark, Q2 is 50th percent mark or median, and Q3 is 75th percentile mark. Interquartile is just a range from Q1 to Q3. The figure shows us the 3 groups of customer type, x-axis, and the product quality, y-axis. We do see now substantial difference across the group. We can also tell that the group 2 has substantially more dispersion, a larger box section in the box plot. We also see where the median is located for each group, and we can find outliers. The outlier is in the first category. Multivariate descriptive displays or plots are designed to reveal the relationship among several variables simultaneously, as was the case when examining a relationship among pairs of variables. There are several basic characteristics of the relationship among sets of variables that are of our interest. It includes the forms of the relationship, their strengths, and the dependence of a relationship on some external circumstances. The scatter diagram or scatter plot is our bivariate plot. However, we can enhance it with symbols and colors to illustrate a relationship among 3 or even 4 variables. Bubble plot can help us display the value of 3 variables at a time using symbol, usually circles, where the value of the 3rd variable is used to determine the size of the symbol. Many data sets include also a mixture of both continuous and discrete variables. Conditional scatter plots allow us creating a multi-panel display where each panel contains a subset of the data, an array of simple plots, but arranged according to the value of some conditioning variables.